In this video, we are going to go through base hydrolysis of esters and amides. So first thing to recognize here is that reacting under basic conditions, our leaving group will be an anion. Now, when you react an ester under base hydrolysis conditions, we're using NaOH, H2O, and heat. We're going to have our slice and dice here. And net result, we're not making a carboxylic acid. We are generating a carboxylate ion. And then we'll have a neutral alcohol byproduct. Now, while the ester is a lower reactive derivative, hydroxide is a good nucleophile that can attack right away and break the pi bond. Looking at our first tetrahedral structure, we keep in mind that we eventually want to kick out the alkoxide, and we then compare leaving group propensity. We have OH minus versus our alkoxide, and those are approximately the same in their leaving group propensity, approximately the same. And because they're approximately the same, let's just go ahead and kick out the group that we need to kick out to drive the reaction forwards. Okay. You could, of course, kick out the hydroxide ion, but that would just bring you back to the beginning. So let's think, because the leaving groups are approximately the same, we will kick out the leaving group that we need to kick out to drive the reaction forwards, which is the alkoxide leaving group. Now that produces a carboxylic acid intermediate, but that's not going to survive. Not going to survive. Our leaving group, the alkoxide, will deprotonate the carboxylic acid irreversibly, okay, producing a carboxylate ion and an alcohol. And that's specifically an irreversible proton transfer because of the differential in the pKa's of the acids on each side of that equilibrium. Carboxylic acid's around 5, alcohol's around 17. So the net result is the formation of a carboxylate ion, not a neutral carboxylic acid. That's our doorstep. That's the bottom of the ladder of reactivity. Now, just a conceptual detail here. This reaction is called saponification. Saponification, if you ever hear saponification, you're thinking that's base hydrolysis of an ester. It's also the process that occurs every time you wash your hands. When we have fats on our hands, fats in the form of triacylglycerols, are esters. And when you wash your hands, the base hydrolyzes the ester, producing carboxylate ions, aka fatty acids, and then those are sloughed off as we wash our hands. So we're doing saponification all the time. At least we should be, right? This is a public service announcement. Wash your hands, get on that saponification train, right? No joke. It's important. Wash your hands. Saponify. Let's now imagine reacting under base hydrolysis conditions with your amide. We would react with NaOH, H2O, and heat. We will slice and dice, making our carboxylate ion, and then we have a neutral amine byproduct. Right? Mechanistically, we are going to attack right away. Hydroxide is a good nucleophile. In the first tetrahedral structure, keep in mind that we eventually want to kick out the nitrogen here. But right now, the best leaving group is OH minus. Okay, so what we have to do is deprotonate that OH group to decrease its leaving group propensity. Now, that creates this dianion intermediate, and that's a little bit funky because we're not used to seeing two negative charges in the same tetrahedral structure, nor are you used to seeing two positive charges in a tetrahedral structure. But here the idea is we have to create that dianion intermediate to kick out the nitrogen of negative charge, which is a really poor leaving group. When we have that double negative here, we're essentially having so much electron repulsion that we're going to collapse and eliminate the nitrogen of negative charge leaving group to reduce the electronic repulsions that are present. Okay, now that would form the carboxylate ion directly. And then the nitrogen of negative charge, your leaving group, is then going to rapidly deprotonate water in your mixture. Water is the solvent. It's going to undergo a very exothermic proton transfer step and irreversibly deprotonate water, forming a neutral amine and hydroxide. So while we kick out a nitrogen of negative charge, the nitrogen of negative charge, being hella basic, is going to deprotonate water, forming a neutral amine, such that we have a neutral amine and a carboxylate ion at the end of the reaction. Okay. Now, that dianion intermediate, again, a little bit funky, but we do create a dianion intermediate in the base hydrolysis of an amide. We did not need to create the dianion intermediate in the base hydrolysis of the ester, because in the first tetrahedral, the alkoxide and OH minus were approximately the same. So I could just go ahead and kick out my alkoxide leaving group, which then irreversibly deprotonated the carboxylic acid intermediate. But in base hydrolysis of an amide, after we attack, we then need to deprotonate the OH component, creating the dianion intermediate. We then eliminate the nitrogen of negative charge, and then that very rapidly, irreversibly deprotonates water to form a neutral amine. Now, just in case you run into this, another conceptual note here is that when we do this reaction, and really anytime we're reacting under basic conditions and you have a counter ion, that counter ion kind of tracks along, following around the negative, like a puppy dog, right? So there's a chance you might see on an exam the O minus paired with the Na plus, or you might even see this, O and A, essentially showing them associating. We more accurately produce a carboxylate salt. A carboxylate salt. All right, this has been base hydrolysis of your ester and your amide. Under basic conditions, we have an anion leaving group, and base hydrolysis is net result irreversible in each of those situations.